first of all, we have to handle a very basic problem. When you ask yourself, or a student asks you, how do you take a picture of a black hole? Why haven't people taken a picture of a black hole before? Well, the problem is that there is a very basic problem, and that is black holes are the most compound objects that we know. In addition, all the black holes we know are placed at astronomical distance in our branch number. And of course, this stops after one rotation, because once you go back, you will not gain any more information. And what you should appreciate is that ideally, this little white square should be filled with color. Only then we would have a full and complete coverage of the UV space, and only then we would have a perfectly sharp image, which of course we are very far from having. So this is exactly what has been done in 2017. As you can see, these are people that have gone to different observatories. This is in Mexico, this is in Chile, at the South Pole. It's been computed that about 4.5 billion people have seen the image in the first 24 hours. Now, 4.5 million means the large majority of human population. And that essentially also means that unless you were in a cave or completely drunk, you probably have seen the image on the first 24 hours. The reason why the image was so widely diffused is still under debate. This is something that sociologists are now working on. My interpretation is that it really was the fact that the image was captured by the social media, and as a result of this has become and spread very virally. As you can see, here are some interpretation of what is it that we are actually seeing. Just to cast things in the proper dimension, sometimes in astronomy we tend to think of a reminder of the scale. This is the image of M87. This is our solar system. So the whole solar system fits perfectly well within the brightest impression, this darker region over here, and Voyager 1, which is the farthest away satellite, is just now entering into this bright region. So M87 is a huge black hole, huge even in terms of physical spatial size. So these are the what you can see as the simulation we start is that accretion is a stochastic process. It's not a steady process. It's a bit like the beautiful waterfalls that you have in this region. Water comes in, but doesn't always come at the same rate. Sometimes comes at higher rates than other times. And what is important is that this then produces fluctuations in the disk, and therefore also in the emission. This is the inclination at which we think we are seeing M87. And now we will see the same picture, but in terms of the emission. So now we are looking not at density, but at brightness in 1.3 million years. So you can see that if you had eyes that were sensitive to this radiation, you would see essentially an axisymmetric ring. But it is deceptive. As a matter of fact, this radiation field is far more complex, and I will explain why. And of course, you have to bear in mind that this is not this is the image produced by a computer. A telescope would see something very different. And this is what a telescope would see, an image of a ring which is flickering over a time scale of a few seconds, well actually a few seconds in this simulation of a few days in real time. And this is what we have actually observed. So you can see that we already have, by using simple first principle consideration, already have a reasonable understanding of what is it that we should expect. We should expect a ring of light. We should expect this ring to be circling a depression, a darker area, and now we'll explain why it creates it. And to make things even more interesting, you will see a high order image also from photons that are coming from the lower parts of this sheet of light. Okay? And so the picture that you would normally see of a black hole is something that looks like that. So this is probably something you have seen already. This comes from the film Interstellar. Now you probably understand why Interstellar shows you this disk over here. The first part over here, this is the part of the disk where the astronauts are reaching. This is the part of the disk behind the black hole. This is the part of the disk below. And This picture is very accurate, either two important flaws, but otherwise it's very accurate. And the most important thing is that it teaches us a very important lesson. If you have to hide, don't go behind a black hole, because that will not help. Now, the flaws are for two reasons. The first one is that the disk, as I explained, cannot be geometrically thin. We expect the disk to be geometrically thick, it can be optically thin. And another important thing is that the disk will depend, the shape of this will depend on the inclination of the observer. So this is a more realistic representation of interstellar, and you can see that if you are, as of now, seeing the image exactly face on, then you will see it perfectly symmetric. There is no preferential direction. But as soon as the inclination is different from zero, then there's going to be one portion of the disk which is coming towards the observer. This produces a relativistic Doppler boosting, and therefore there's going to be always a region where light is going to be brighter. And so the expectation, the general expectation is that an emitting black hole, unless it is exactly face on, will have an asymmetric rate of emission. Now, the image, let's go back to the, is this portion over here, this central depression. Okay? This is often confused with the event horizon, but of course it is not. The event horizon is a null surface, cannot emit any light, cannot be observed in any manner. So what we are seeing really here is the shadow. And again, let me give you an example using an analogy. Suppose you have a black hole, and this black hole is placed in front of a source of light, say a stellar field. Then there's going to be photons which are emitted from the source. They will reach the black hole being parallel, and some of these photons will enter the event horizon right on. They will immediately hit the size of the event horizon. Of course, they will be absorbed. But then there are going to be also photons which are going not to hit immediately the black hole. They will be in a certain region. This region is dictated by the photon unstable circular orbit, and they will also eventually be absorbed. And so if you are an observer at a large distance, you will see a shadow. The shadow cast by the presence of a black hole. And just to remind you of the sizes, for a Schwarzschild black hole, non-rotating black hole, the horizon size is twice the mass. The unstable circular photon orbit is 3 times the mass, and the radius of the shadow is essentially the impact parameter and the circular orbit, and it is about 5.6 times the mass. This example also helps me to explain a point that may be not so clear. We've seen that this region is not the event horizon, it's just the evidence that the region is event horizon. But also, this region doesn't need to be black, completely dark, as you would expect from an event horizon. The reason is that, suppose that you have a photon emitting exactly where I have my pointer. This photon would have no problem reaching the observer because there is nothing absorbing it. Of course, a photon emitted here would encounter the black hole, but a photon emitted here would not have any problem. And that is why the region inside the bright ring is just showing a depression in intensity and is not necessarily dark. So, how do you study this problem? Well, you have a large space because essentially we don't know much about what's going on near a black hole. So, first of all, we need to simulate different space-time properties, black hole mass and spin, black holes in other theories of gravity, alternatives to black holes, whether they are without an horizon, they are comparably without an horizon, or without a surface, with or without a surface. So there is a huge zoology of possibilities. Then we have to study the properties of the plasma, and there too, the plasma has different behaviors according to different properties, in particular on the strength of the magnetic field. We have 2 main types of accretion. One is called SAME, and one is called NAV, depending on the strength of magnetic field and the amount of magnetic field is accreted. And then, most importantly, we need to specify what are the properties of the light. We know almost certainly that the light that we receive at 1.3 millimeter has to be of synchrotron type. But what is producing this light? Well, this is a much more complex problem. And what are the properties of the plasma that is producing this light is an equivalently difficult problem. So let me spend a slide on this, because I think it's a very different, you can play around with the inclination of the observer. And so for each of these simulations, you can build thousands of different images. Okay? And you can see that there are situations where, like here, there is a very large shadow, very, very small shadow over like over here. So depending on the property of the plasma, you can have very different images. So one thing that I would like you to reflect is when we see an image like this, and notwithstanding all the complexity in going from a radio observation over to producing this image, we ask ourselves, where do the photons come from? Does it mean that because I see light over here, there is a photon in the disk? Well, that's very, very hard to tell, because this is a two-dimensional projection of what radiation is. Just to give you an example, I can take the same simulation, the very same black hole. This is, let me explain this a bit better. This is a section over the disk. This is the vertical direction. This is the photon circular orbit. We have stable photon circular region for a rotating black hole. It's not just a sphere, it's a more complex surface. This is the innermost stable orbit. And this is if I use R high equal 10, I put a lot of temperature in the disk, you see that most of the emission comes from the disk. Vice versa, if I use, for the same simulation, I put R high equal 160, I would see that most of the emission actually comes from the jet, from the sheet of the jet. This is for the same simulation. It's true, the same is pretty much true also if you have a mad simulation, although in that case the distinction between disk and jet becomes even thinner. So when we look at images like these are 4 images of 2 mad simulations with different R high, and these are 2 same simulations. And if we ask ourselves, okay, where does light come from? Because these are synthetic, we have produced them, we can distinguish the light coming from the disk from the light coming from the disk, the light coming from the disk from the light coming from the jet moving towards us, and the jet moving away from us. So we would have a matrix of contributions, and this is the result of this matrix. So in this case, most of the light, you can see 90+% comes from the disk. Very little comes from the forward jet, even less from the backward jet. But if you are in a situation like this, well, quite the opposite. Very little light comes from the jet. Most of the light comes from the, very little light comes from the disk. Most of the light comes from the jet, and surprise, the majority of the light actually comes from the receiving jet, the jet moving away from us. So this is an example, I think a very exemplary example of how it's very hard, once you have an image, just to determine what is the actual origin of the light. So we have produced one image of a person, and it's a very blurred photo. And we want to ask ourselves, who is this person? And in order to answer this question, we go to the security manager of the stadium, and she's a lady, and she says, yes, of course I can help you with this. Give me the photo. We'll just put it across all of the photos that we have collected of all the people who went to the stadium. And that's what the software does. It cross-correlates all of the images of the people who entered the stadium with the image that we have provided. And at the end of the day, provides this answer. Says, okay, these are the 10 top best matched images. And you would say, well, I'm a bit disappointed. I don't know who is this person. And the security manager would say, of course you don't know much about statistics. I cannot answer your question. Given the quality of your data, I cannot answer your question. However, you should not be sad, should not go away sad, because you already have learned a lot. Because what you've learned in particular is that the person that you're looking for is most likely a woman, because all the top best matches are women, and also that this person most likely has a long hair,
because all of the top 10 best matches have long hair. So the person you're looking at cannot tell who she is, but my bet is that it's a woman with long hair. And this is pretty much the logic that we have followed in obtaining and interpreting our results. We have obtained some information, which is not the most stringent information, but this is all information we can obtain given the quality of the data. So, just to give you an example, this is on the left, you have the observations from M87, I don't remember which day it is, and this is a theoretical model which matches extremely well, as you can see, the observation. Because we know everything on what is on the right side, you may think that you know everything on what is on the left side, but this is not the case, as I've shown you with the example of the stadium. More precisely, the bottom are 3 images which are obtained that give equally good match with the observation. So you can do this very precisely and rigorously mathematically. You can calculate what are gauge-independent measures of how much are 2 images different from each other. And the images at the bottom, they are all equally good, but they correspond to 3 completely different black holes. This black hole here in the middle is a Schwarzschild black hole, a non-rotating black hole. This is a curved black hole, maximally rotating, but with a mag type of accretion and a high equal 10. And this is a counter-rotating, maximally counter-rotating black hole, -0.94, with a high I of 80. This is the geometry that we have encountered, and I don't think it's resolvable. Essentially, because we don't have all the information on the energetics of the electrons, we cannot exactly know what are the properties of the electrons, so we cannot really distinguish one image from the other. So these geometries are present, they are inevitable, and this is both good and bad. If you think about the example of the stadium, the good thing was that although we didn't know the person, we were almost certain this person was a woman with long hair. And here too, the fact that all of images match with those of a black hole tells us that we are very confident what we're seeing is a black hole. The bad thing, of course, is that we are not sensitive to some aspects. In particular, in the case of black holes, we're not sensitive to the spin, at least with the present observation. So, in fact, in our paper, we have not ever measured or claimed a measure of the spin of a black hole. We have provided some suggestions about possible values, but we never measure that. Now, what have we, remember I said that in 2017 we've taken data both from M87 and for Sagittarius A star. And actually Sagittarius A star was our first choice. We wanted first to study Sagittarius A star. But then it became very clear, very rapidly, that Sagittarius A star is a much more difficult source to analyze. And that is why we postponed the analysis of Sagittarius A star after we were able to measure M87, and it took us 3 years more to actually get some answers for Sagittarius A star. So what are the disadvantages? The first one is that it's very simple. Sagittarius A star is at the center of our galaxy. If you want to look at the center of our galaxy, you have to point in the direction where there is a lot of intervening matter. This is the interstellar matter, this is the dust, another material that has as an effect, intrinsic effect, that of scattering the path of light. And so we suffer from intrinsic scattering, which means that if you have an image which is sharp on the left, just because there is scattering, and we don't know exactly if it's scattering, if it is a static scattering, a dynamic scattering, where the scattering is located, if it is integrated, if there is a precise region where there is a scattering, doesn't matter. The point is that some details are intrinsically blurred by this scattering. The second and most important drawback is that of variability. I remind you, we try to make an observation of a time scale of a day, of 24 hours. Actually, we're observing much less. We're observing about 10 hours. And over 10 hours, Sagittarius A star is changing all the time. This is a movie that shows in real time. Look at this. This is a real-time clock. The actual variability of the accretion flow. So it is like taking data of a subject which is continuously moving and changing. And so you have to be able to distinguish features which are permanent from features which are instead just changing because of whatever stochasticity in the activity. And then, of course, this is a real image of the visibility space. You can see that we have very poor information. The amount of data doesn't allow us, even though we have the best possible resolution, doesn't allow us to have a very sharp image. The advantages, on the other hand, is that we know the mass of Sagittarius star extremely well. It's 3,957,000 solar masses. Now, this is a point of precision. You may, as a matter of fact, if you convert this precision to the knowledge of your mass, so your weight, body weight, this would correspond to knowing your body weight with a precision of about 50 grams. So I don't know how many of you know your body weight with 50 gram precision. I certainly don't. But this is the precision at which we know the mass of the star. We also have been observing this object at many other wavelengths, at radio, the infrared, and the X-ray, and also during the observations themselves. So we were looking in the radio, but also these different wavelengths through multi-wavelength campaigns. So we know the variability in other wavelengths, just as we know the variability in the radio. Just to give you an example, this is our typical observation frequency, 230 gigahertz. This is at lower frequencies, and this is in the infrared. So in principle, we have images not only in the radio, but also at these different wavelengths. And so we have more constraints that we can place on the actual image. So in total, we have 11 constraints because we have to match all of these different pieces of information. And in the case of M87, we had, if you remember, 4 images and 60,600 images. In the case of Sagittarius star, the numbers explode. We have 9,000 observed images. So these are 9,000 images which are compatible with the data. And we have built a database of synthetic images which is 5 million high. So, in a nutshell, what you find out of this comparison is that none of our synthetic model passes all of the constraints. Okay? The most models are too variable, or those only slightly. So, if you just lower the constraint of variability, then a number of models match all of the constraints. And these constraints tell us that most likely the accretion time is of mag time, that is magnetically dominated. It is from a black hole which is spinning in the prograde direction, so positive spin, has a low inclination, again like M87, we see it almost face on, and as far as the RI, it is of order 160, which means for us they are cold electrons. On the other hand, we can also exclude those that really are badly matching the data, and these are retrograde, spin, edge on, and single temperature. So these type of models very clearly are in contradiction with our analysis. So these are the two black holes now, side by side, and it's amazing how, and they are in scale. So if you were to go out tonight and look at them, you can't quite do that because they are visible in different hemispheres. But if you were able to do that, that's what they would look like in the sky. And they are almost the same size. Sagittarius is slightly larger. And the variability, essentially, you can see it over here. In the case of M87, essentially, we have about 30 images which are compatible with the data. The mass is of more than 6 billion solar masses, and the variability is of more than 24 hours. Vice versa, in the case of Sagittarius A, we have 9,000 images. The mass is about 4 million solar masses, and the variability is of the order of a few minutes, tens of minutes. Okay, I will spend a few remaining minutes in discussing gravity. Well, the concept in our analysis, we take the size of the shadow, we approximate it with a ring of a given diameter, and we measure the diameter of the ring. And we correlate this is correlated to the intrinsic diameter ring modulo a calibration factor alpha c. This is a factor which takes into account calibration errors, variability in the source, and all sorts of technical aspects of the imaging rendering. And this size of the shadow is then converted to a deviation from the shadow size in the case of Schwarzschild. So it's 1 plus delta. And so delta is the deviation away from Schwarzschild. And the projected size in the case of Schwarzschild is 6 square root of 3. So delta is a fundamental question, a fundamental measure that tells us how large is the deviation away from Schwarzschild, not necessarily from general relativity. Okay? Delta is non-zero already in general relativity. It would be 0 just if it was a perfect Schwarzschild black hole. And just like in the case of the images of the women, we don't have a single value of delta. We have a distribution, probability distribution. And this is shown over here. So this is the probability distribution of delta, and this is the blue stripe is what is allowed by general relativity. As you can see, these are all negative numbers because Schwarzschild has the largest shadow, and this is the probability distribution function. And you can see that the peak of distribution is very well with what expected from general relativity. The green is the same analysis done for M87. Once again, it's not as good, but it is pretty much close with a 10% difference with respect to what is expected. You can transfer this also in this other different violin plots, where here you have the mass of the object and the deviations delta is shown on the vertical. However, this is reassuring, but it is not the end of the story. Are there other options that are consistent with this interpretation? And of course, given that the uncertainty is so large, alternative explanations are possible. And if you think about it, this is inevitable in a science like astronomy, where you cannot really set up an experiment. All you can do is observe. And therefore, how do you go about testing reliably when there are hundreds of alternatives that are available to explain the very same observations? Well, there are fundamentally two approaches, and we have considered them both. A first approach is an agnostic approach, where you say, I don't know what theory I'm talking about, but I'm just making a measurement, and then I'm converting this measurement into some set of parameter values, and then this means that any theory that is able to reproduce these parameter values is consistent. Or you can do an agnostic approach, whereby you say, I look at a specific theory or a number of specific theories, and I start comparing one by one. And in this way, you can either accept a theory as compatible or reject it because it's incompatible, or restrict the validity of that theory to certain parameters. Let me first tell you something about the agnostic approach. It is something where I spent some time thinking about it. The important thing here with respect to binary system of gravitational wave emission, which I also spend a lot of time on, is that here we don't need a field equation. All we need is a background metric, because essentially the mass in the plasma and the mass of the photons is negligible with respect to the space-time curvature. So all you need is really a metric in a given coordinate system. And then you can think of writing a metric which is written in this form, where you have a metric representation in a given coordinate system plus additional coefficients, AI's and BI's. And essentially, you can think that the general relativity is seen as a special case of this more generic metric where all the coefficients are set to 0. And this expansion has been expressed in terms of non-rotating black holes first, in what is called the RZ metric, and then for rotating black holes in the KRZ metric. And essentially there are two tricks in this approach that make it so powerful. The first one is that there is a coordinate compactification. So instead of thinking of coordinates, the radial coordinates are going from, say, from 2 to infinity, we here go between 0 and 1. So all the metric functions are evaluated between 0 and 1, and this makes the comparison and the expansion much simpler to compute. The second one is that no matter what, you will have poles, you will have singularities at the horizon. And so the best way to approximate these singularities is using a fast convergent series expansion near a pole, and then it's a Faraday expansion. So particularly we use a continuous fraction approach. This is one of the metric functions. This is the GTT metric function, and you can see that we express onto compare object with a surface like a ground star, and we have considered charged black holes where charges here are really meant to be hairy black holes with different properties and layers. So let me give you an example. Because the infrastructure that I've explained to you is completely generic, it's not too difficult for us to move from one black hole spacetime, say Kerr, to move to another black hole spacetime, say Dyson black hole. That's exactly what we've done here. We have carried out simulations. We have tried to match at least one of the properties between two black holes. In this case, we have matched the innermost circular orbit. We also matched the horizon side. We matched the photon orbit. It doesn't really matter. What you can see is that the two simulations have differences. Of course, they have to have differences. GRA is a deterministic theory. But the point is not so much whether there are differences. The point is, can we measure these differences? And so, can we actually produce images which are sufficiently different? And that's the result. This is a Kerr black hole on top, and this is a Dyson black hole of the same mass. And they are different, but they're also extremely close. And if you add scattering, say like in the case of Sagittarius star, that's what you would get. So how confident are you of being able to tell this from this image? Essentially zero. And that is why right now our understanding is that different black holes in different theories are extremely hard to tell apart, unless the black holes themselves have very large differences. In the case of the Dyson and the Kerr black hole, this is not the case. What about boson stars? Well, boson stars represent self-gravitating condensation. They are very appealing because they could explain dark matter, for instance, in the center of galaxies. These are objects which are nominally infinite in size, but they are very compact at the center, and usually do not have a surface. So we can do exactly the same. We can take an accreting torus spread by magnetic field and see what happens when they accrete onto a boson star. Of course, this is what I'm showing you in this simulation. Just for the record, we consider non-rotating boson star, and really the simplest type is what is called a mini boson star. This is a complex current field in the quadratic potential. So here is what happens. You see, this object, I'm not showing you the boson star because I'm not showing you the star field here, but I'm just showing you the matter. And you can see that the matter goes right in. There is no surface, there is no eventualizing, blocking or absorbing matter. And so matter can go almost at R equals 0. It doesn't go to R equals 0 because as it goes further down, it will encounter a centrifugal potential, a centrifugal barrier, and so we'll just actually move out of the equatorial plane. What we actually observe is that these objects produce an outflow in the vertical direction. So you have to imagine that the horizon, if you consider black hole the same mass, the horizon would be well outside of this innermost torus. The mini torus, we call it, is the object that is produced by the matter that accumulates as it's coming from the outer torus. And so you can easily imagine that this object will show a depression because there is still a region where there is no light, because there is no matter, but this size will be very different. And this is shown here in this imaging. So this is a Kerr black hole, this is a boson star. You can see already from this image that the size of the shadow is much smaller. And if you then blur it with the sensitivity of a telescope, you can see that this is a much smaller size. Of course, you can always increase this size by just playing around with the mass. In the case of M87, then you have quite a bit of freedom there. But this mass increase, even in the case of M87, would be too large to match this size over here. You would need to increase the mass, and you would be inconsistent with all sort of other observations. So What this has led to us to conclude is that boson stars, at least of the type we have considered, are distinguishable from black holes, and the reason is the one I've explained. Matter will be able to go right in and then mix even in innermost regions. What about a black hole mimicker with a surface? Okay? Like, for instance, a gravel star. These are very fascinating objects. Of course, if this object has a surface, matter that accretes onto this surface will be emitting light itself. And this radiation will be thermalized and be emitted. So it's very easy to compare the spectral emission from such an object. This is what is shown over here. This is the spectrum frequency, and this is spectral density. All of these points are the data, such as this is the radio, this is the X-rays and gammas. And what we have done here, we have considered we have placed a surface at 2.5 m, so slightly outside the event horizon, and we have changed the accretion rate. And these are the expected spectrum from the different accretion rates. And as you can see, they are nowhere close to what we observed. You can also change the position of the thermalized surface, and here you go from 8 to even 2m. And again, what you do is you go to higher frequencies, but you do not really match all the low energy tail. Okay? So it's very, very hard in terms of basic principle of what we know about accretion to explain, use these objects to explain, something related to spectral image. But you can still say, well, no matter, gravel stars anyway are such fancy objects that they will not thermalize matter, they will not produce a thermalized spectrum, so your considerations are not valid. But still, this surface will have a certain amount of reflectivity. Some of this matter will have to be reflected. So even if you stick to one single wavelength, the one we have observed, a reflecting surface will show up differently. And we measure this in terms of this quantity, the albedo, A, and A equals 1 is a full reflection, and A equals 0, of course, is a black hole because it's full absorption. Okay? And this is an image of a black hole, and this is the blurred equivalent for a given inclination, just to give you an example. You can see that for A equal 0.1, it's very hard to distinguish a gravel star from a black hole, which would be this one. But if you start having a reflectivity which is more realistic, of order 0.5, then you can see that there are differences between a black hole and a reflecting surface. So while this again doesn't give you a conclusive answer, our evidence is that once again, none of the objects we've seen looks like a gravel star. Well, what about black holes in different theories, or black holes in Einstein theory that violate the no-hair theorem? Well, we can use the size that we have measured and its uncertainty to constrain the possible values of these hair or these charges. So this is what we have measured, the shadow size, 4.3, and given the uncertainty, you can think that this quantity provides you a measure, allowed measure, which is this one over here. And of course, Schwarzschild black hole will be exactly this dotted line over here. And then you can calculate all the variations of the shadow radius and over to gravitational physics and geometry. Over the last 5 years, 6 years, we have studied accretions of black hole more intensively than we've done over the last 30 years. And there are many things that we have learned over these years. And but there's still a number of things that are needed to be discovered and understood better. In particular, the fact that all of our simulations are way too variable with respect to what we see. And while we have some suspicions about what is the source of this difference, there is still an understanding lacking. We are also starting to explore alternatives to curved black holes. Boson stars can be distinguished very clearly, other black holes cannot. And what one can do is one can try and constrain what are possible charges of different black holes. If you ask me what is the important contribution that EHT has provided? Well, for sure, what we have shown is that there are at least two galaxies whose center there are supermassive black holes. If you think there are billions of galaxies, well, it's a long way to extrapolate it to all of the billion galaxies. But at least in two cases we show that that's the case, and this is a very important tile in our understanding of the universe, because all of our understanding of the universe presumes that at the center of galaxies there is a supermassive black hole. However, if you really ask me personally, what is the most important contribution? I would say the most important contribution has been that of transforming the event horizon from a concept to a testable object. If you remember when studying science the first time, you were exposed to the scientific principle, the possibility of formulating an explanation for a phenomenon and testing whether your explanation fits the actual experiment or not, so that if it fits, provides an explanation for the experiment, and if not, it's to be ruled out and you need a new and better explanation. Well, so far, up until now, we were not able to do this in the case of an event horizon. This was something that was just too slippery to be tested. But by now, through the Event Horizon Telescope, we have changed this, and this is, in my view, the most important contribution. Thank you for your attention.